Hi everyone and a warm welcome to today's session. So this is going to be our lecture number 8 on time series analysis and forecasting. So if you are following my playlist for a while, you will know I have covered all the important covariant stationary processes one by one. So I have discussed what is white noise process, what is autoregressive process, moving average process, and in the previous video I have described what is ARIMA, that is autoregressive moving average process. And this is going to be our last session in this topic of important covariant stationary processes, where we will discuss what is ARIMA and what is SARIMA. And with that we will end this topic of important covariant stationary processes. But before understanding what is ARIMA and SARIMA, we have to know something called the difference operator. Right, so let us start understanding what is a difference operator. Difference operator is denoted as this. This is the symbol of difference operator. So what we say is that if you apply difference operator on yt, what does that mean? That will be simply yt minus 1. So basically power is, so the degree or the power of this difference operator is 1, so the maximum lag value is 1. So what will happen if I say delta square yt? Delta square yt is nothing but delta times delta yt, right? Now understand something. What can you write this? You can write this into lag operator of yt. So this will be simply 1 minus L into yt, right? So from here, what can you say? Delta yt you got as 1 minus L into yt. So this basically means that delta is simply 1 minus L, right? Delta is simply 1 minus L. So from that, if you apply here delta, what will be delta yt? Delta yt, you can write it in two ways, yt minus 1. This is one way. So delta yt minus delta yt minus 1. So this will be simply yt minus 1, yt minus 1 minus yt minus 2, or yt minus 2 yt minus 1 plus yt minus 2. So this is one way of doing this, or you can use this formula also. So if you want to find out delta square yt, you will simply write this square into yt. Now if you apply the formula of whole square, this is what you will have: yt minus 2 yt minus 1 plus yt minus 2, right? So this is the same thing that you have got here. So what I am trying to tell you is that what is the difference operator, because you will see in a while that in order to define ARIMA and SARIMA, you will use this difference operator multiple times. So depending on the degree, you have to write in this way. Delta, this is the, the operator, this is the sign of the operator. Difference operator, if you apply it to yt, this will what will you get, right? So delta square yt is this. I hope this is understood. It's pretty simple. Now the next operator that we will talk about is the seasonal difference operator. What is seasonal difference operator? Simply this. And then if you apply it to yt, what you will have is that yt minus s. Simple. So seasonal, here s is for seasonal, right? In order to define seasonal ARIMA, you need this seasonal differencing operator. So this is simply delta, and in suffix you have s yt. Basically you are taking the difference of the seasonal lag value. So s here is the period of seasonality. So if you have seen my lecture on classical decomposition of time series data. Then also there I have mentioned what is seasonality. If you haven't watched that video, I'll give the link in the description. Please watch that video. So this is basically the period of seasonality, yt minus yt minus a. So you are taking the lag value from the period of seasonality. So subtracting the value of yt from the lag of period of seasonality. So this is what you will have. So this can be written as yt minus, using the lag operator, so 1 minus this into yt. So delta S is nothing but 1 minus ls. Right? In the previous case, what we got is that delta is simply 1 minus L in case of difference operator or differencing operator. But in case of seasonal difference operator, you will have something like this. Now if we know differencing operator and seasonal differencing operator, we can define ARIMA process. ARIMA, here this I is extra. AR we all know this is auto-regressive process. MA is moving average process. Now you have something extra called I. So the full form is auto-regressive integrated. I stands for integrated. Integrated moving average process, right? Auto-regressive integrated moving average process, and here the number of parameter is increased. So this D is it stands for differencing, and let me write the model formula, you will understand. So a time series process yt is said to follow ARIMA process of order PDQ if this difference, the power of this difference or the degree of this difference is D, yt. This distribution follows ARIMA PQ. This follows ARIMA PQ. So ARIMA, I have talked about ARIMA model, ARIMA process in the previous video. I would request you to see that video first, then come back to this video. So if you apply this delta operator and take the order or the degree to be D, so for that reason here this parameter D comes, so that you are taking difference D times. Basically that is what I have shown you here. Here D is 2 basically. So delta 2 yt means you are applying the difference operator 2 times, right? You are applying it 2 times. Now in general case, when you write PDQ, it means that you are applying the difference operator D times. So delta D yt. Now if this follows ARIMA PQ, then you will say the original yt will follow ARIMA. I know it might seem a little difficult to you as of now, but it's pretty simple actually. If you think about this, I'm saying that the original yt will follow ARIMA with parameters PDQ if and only if you take the difference operator and apply it D times, apply it small d times on this original yt, and if you see that process follows ARIMA PQ, then we will say the original yt follows ARIMA PDQ, right? If you have any questions, any doubts, you can let me know in the comment section. Now for simplicity, what I can do, I can assume this to be equals to say some yt star, right? Yt star is this operator to the degree into yt. Now, so what will be the value of yt star? Yt star can be written as alpha plus phi 1 yt minus 1 star. Now everything I have converted every y in terms of yt star. So since this follows ARIMA PQ, I am writing it in the form of ARIMA PQ. Yt minus 2 star. This will continue up to yp yt minus p star. And then you have MA is the same, MAQ. There will be no change in MAQ. So theta 1 epsilon t minus 1 up till theta q epsilon t minus q, where epsilon t follows white noise 0 sigma square, and these are all constants. I am not writing it again. You know by this time that alpha, phi's and thetas, these are all constant terms, and epsilon t follows white noise 0. So this is basically the definition of ARIMA process. ARIMA is what? If you in the original process yt you apply the difference operator d times, that is why this parameter d comes into the picture. And if you see that follows, that process follows, this modified process follows ARIMA PQ, that is, it is in this particular format. So here you have this ARP terms and then you have MA terms, so ARIMA PQ basically. If you can express this new distribution in the ARIMA PQ form, then you will say the original YT will follow ARIMA BDQ. I hope this is absolutely clear to you. Now again, we will write it down in a compact way as we always do for any other processes. Write in the lat form L square YT star, and this will go up to 5p L to the power p YT star plus epsilon t plus theta 1 L epsilon t. This will go on theta q L to the power q epsilon t. So basically what you can say here is that 1 minus phi 1 L minus phi 2 L square phi p L to the power p into YT star is alpha plus 1 plus theta 1 L up to theta q L to the power q into epsilon t. So again we consider this to be this into YT star. By this time I hope you know how I am writing this. Again I am giving the link of the playlist, entire playlist in the description. Check that out if you are new on my channel. So this is what you can write. And again this is the characteristic polynomial. This is also the characteristic polynomial, right? This I have explained to you multiple times. Characteristic polynomial of the AR part, characteristic polynomial of the AR part, and this is the characteristic polynomial of the MA part, right? This is what we have. Now we can simplify it further. We can write it in this way: alpha upon phi L plus this upon phi L into epsilon t. So simply what I have done, I have taken this and I have divided this. This comes here. So individually I can write this. So YT star is some, consider this to be some mu plus and this to be some xi L epsilon t, and this is the compact form of ARIMA PDQ, where this mu is nothing but alpha by phi L and xi L is a function of L only. This is the ratio of the characteristic polynomials. This. So this is basically the entire definition or description of the ARIMA that I wanted to share with you. So here only another parameter comes into the picture. The rest of the things are exactly the same. Only in the original process you are applying the difference operator and the degree of that difference is d. And if you see that follows ARIMA PQ, then the original distribution follows, or the original process follows ARIMA. This is the general form of ARIMA, and in the lag term, lag version, this is what you have. Okay, I hope this is understood. Now quickly let me go to the SARIMA. SARIMA, and it looks even more dangerous, but it's not. This term we are familiar by this time. This comes from directly from ARIMA PDQ. But here you have another set of parameters, capital P, capital D, capital Q, and these three parameters come only due to the period of seasonality. So this second portion in the SARIMA model is only due to the existence of seasonality, and this is not applicable for all the data sets. Only in the data sets where you have seasonality, this portion comes, this parameter come. Otherwise you will have only these three parameters, right? So let us define again. A SARIMA, a time series process YT is said to follow seasonal ARIMA. SARIMA is seasonal ARIMA. This is a seasonal. And ARIMA is auto-regressive integrated moving average process. So YT follows seasonal ARIMA or SARIMA process of order PDQ, capital PDQS. If what happens is that here we will have seasonal differencing operator as well. So this is like this. This follows SARIMA, PQ, PQ, S. I know it's looks very complicated, but again I'll say if you think about this, you will not find it difficult. So it basically says here on the original process you have to apply both the seasonal difference operator and also the differencing operator. If you apply both these operators on this original process yt, and if you see this modified process follows SARIMA with parameters PQ and capital PQ S, then you will say here D is not present because we have already applied this D here on the operators, right? D is the capital D is the degree of the seasonal operator, seasonal differencing operator, and small d is the degree of original differencing operator, right? And if you use this and apply these two operators on the original yt, and if you see that process, this modified process follows SARIMA PQ capital PQ, then you will say that yt follows SARIMA PDQ PDQS, right? And how will you write this? You will write in this format, and what I am writing right now, it's very important because the question is coming from this portion only. Alpha plus phi s this into epsilon t. So this is the original form of SARIMA model. Here what I have done, capital phi SL into capital phi L into yt is alpha plus capital theta SL, capital theta L into epsilon t. Now you know this and this. This is the characteristic polynomial of the AR part, and this is the characteristic polynomial of the MA part. Now in this model we have introduced two more characteristic polynomials. This is the characteristic polynomial of seasonal AR part. Since you know this is the capital P, this is associated with capital P, so seasonal AR, and here you have seasonal, sorry, this is seasonal MA, the degree is Q, capital Q. I know it's again it's getting a little complicated, but this is how it is, so we have to understand this. So this is basically characteristic polynomial of AR, which we have already seen multiple times. This is characteristic polynomial of MA, and these two are additional associated with seasonality. If and only if the model has seasonality, this will come, otherwise there is no question of writing the model like this. So capital phi is associated with AR, but since suffix says this is seasonal AR process whose parameter is capital P, which comes from here, and here you have theta L, theta SL, suffix is S, which is associated with the parameter value Q. Now in order to give you clarity, I have written the forms of these characteristic polynomial. Characteristic polynomial of AR, this we already know, 1 minus phi 1L minus phi 2L square minus phi PL to the power P. This is characteristic polynomial of MA, 1 plus theta 1L plus theta 2L square up to theta QL to the power Q. These are the additional. This is the characteristic polynomial of seasonal AR. See this form, this will be very crucial. These two forms will be very crucial because they will help you to write the formal process that we will do in an example. So basically this is the characteristic polynomial 1 minus capital phi 1, 1 minus capital phi 1 L to the power S, period of seasonality to the power S, phi 2 L to the power 2S. So seasonality means that the same pattern is repeating after some time, right? So basically the pattern is repeating after every S period. So S, here you have 2S, here you have PS, where P is the capital P, comes from here, and here you have for theta SL, you have the same thing but in terms of theta, capital theta 1 L to the power S, L to the power 2s, and here you have L to the power qs associated with this q. Now if you don't understand any of this, you can see this example that might give you an idea of what I am doing here. So here it says YT follows SARIMA 110 110, and S is the period of seasonality, which is 12. So the question is, you have to write what will be YT, or the general form of YT. That is what we are trying to do here. So here, as I have told you, this is small p, this is small d, this is small q, this is capital P, this is capital D, this is capital Q. So ARP. So what is ARP? ARP is AR1. What is the difference operator that we are using? The power is 1. D is 1. So the difference operator is this. And MAQ is MA here. This is 0. So what can you say from this? This looks like this. YT is alpha plus phi YT minus 1 plus epsilon T. So what will be phi L? What will be phi L? For simplicity, look at this. What will be phi L? Phi L is 1 minus phi 1L, right? 1 minus phi 1L. For MA0, what does this look like? This is simply this. MA0, no lag terms. So what will be capital theta L? In this case, look at this characteristic polynomial. If you see, what will be this? There is no theta terms at all, so it is only 1. So we got characteristic polynomial of AR part, characteristic polynomial of MA part. Now we will go into this 110. Now let's go into this portion, the seasonal portion. So this is basically, so it looks like this. So seasonal AR, degrees capital P, so seasonal AR, this is basically 1. Then you have seasonal MA capital Q, seasonal MA capital Q is given as 0, and what is the operator? Operator, this is 12 and this is 1, right? This is what you have. Now simply find out what will be capital phi SL. Remember, P is 1 here. So again refer to this 1 minus phi 1 LS phi 2 L2S. What will this be? Up till how much we will need to write? Only this, because the P is 1, the P value is 1, so only the lag up till period S will be taken into account. So you will have only phi 1, right? If you see here, you have only phi 1, so this is basically phi 1 L, and here you will have what? You will have 1 minus capital phi 1 L to the power 12. So again check, S is 12, 1 minus phi 1 L to the power 12. And for MA, what will be theta SL? MA has Q to be 0. Check here, what will this be? There is no theta. There is no theta, so only 1 will be here. This is 1. So we got all the characteristic polynomials that we need for our analysis. Now the only thing left is to write what will be YT. So previously I have told you how do you write this. Phi SL phi L into YT is basically alpha plus theta SL theta L into epsilon T. Now you have all these values individually, just put them. So this is 1 minus capital this L to the power 12. This is 1 minus phi 1 L, right? This is 1 minus phi 1 L into yt, and this here you have this is 1, this is 1, and this is also 1 into epsilon t. So now you can multiply. Let me do that. Okay, 1 minus phi 1 L minus capital phi 1 L to the power 12 minus capital phi 1 L to the power 13 into yt, and here you have this. So this is the general form, or you can again simplify. T minus 1 minus capital phi 1 yt minus 12 capital phi 1 y t minus 13 is alpha plus epsilon t. And what does this tells you? So if the modified process follows PQ PDQS, then YT follows SARIMA with 1 1 0 1 1 0 12. So this is the general form. If you have to write the process, this is the general form of the process. So what I have done here is that I have only found out the characteristic polynomials of the AR part, MA part, seasonal AR part and the seasonal MA part, and then I have combined this using the definition. This is the definition. I have told you earlier, in this way you represent SARIMA process. So find out these 4 characteristic polynomials based on your parameters values that are given to you. Here I have taken these values 110 and 110. You can vary this parameter values and check for yourself what will be the general form of SARIMA process. And that is all that I want to share. Let me summarize everything. This is everything you need to know about the processes, important processes that are used in time series. From the next lecture I'll be going into the estimation part. So as of now, I have covered what is white noise process, I have covered what is AR process, I have covered what is MA process, and then the generalized version of it is ARIMA. So ARIMA is basically the combination of AR and MA process, and then if you add another layer to this, you will have ARIMA. ARIMA is basically taking the difference operator to make it ARIMA, right? So ARIMA is more general. ARIMA is the general version of these 3 things: AR, MA and white noise process. So from ARIMA model, from if you vary the parameter values, you can land up to AR model, MA model and white noise. Again from ARIMA, depending on the integrating parameter D, the differencing operator, you can land up to ARIMA. And the more general version, if you add another layer, you will have SARIMA, where seasonality comes into the picture. So if you have the parameter of seasonality, if your dataset shows seasonality, then you have to model the time series using SARIMA. So these models are basically for modeling the dataset. This helps you in modeling the dataset. So, and this comes under the stochastic approach of time series. So in classical approach, we do not use any mathematical formulations in order to model that, but in stochastic model we attach probabilities and distributions in case of modeling a time series, and that is what we are doing right now. And this was everything that I wanted to share with you. Thank you for your time. If you like this content, do like my channel and subscribe, so that my channel grows and I can keep making these sort of videos for you. And thank you for your time. Let's meet you in the next lecture, where I'll be going into the estimation.